My name is Jed Thompson, and I'm a PhD student doing theoretical physics at Stanford University. My work ranges across a few different topics, but my primary focus involves understanding the possible landscape of new particles and forces and designing techniques to potentially detect them. Over the past 100 years, we have learned a great deal about the universe. We now understand that matter is made up of atoms, and we know the basic building blocks of those atoms: protons, neutrons, and electrons. In fact, we know that protons and neutrons are made up of even smaller particles called quarks, and we understand how all those particles interact with each other through the four fundamental forces: electromagnetism, gravity, the strong force, and the weak force. Collectively, all this knowledge about fundamental particles and forces is summed up in a theory known as the Standard Model. The Standard Model is an extremely successful theory and has been tested to extremely high precision. But there are several open questions. Much of my work is at the intersection of two of these: the nature of dark matter and the strong CP problem. Dark matter is a term we physicists use to mean stuff that we cannot see, but whose gravity we can feel. When we look out at the universe with our telescopes, we measure that galaxies are spinning faster than we would expect. This is an indication that galaxies are much heavier than we would guess from the stars and interstellar gas that we can see. Whatever makes up the rest of this mass must not emit light. If it did, we would have seen it already. And so we call it dark matter. But this is quite unsatisfying. And as scientists, we want to understand what dark matter is actually made out of. The strong CP problem is a bit more subtle. The quarks inside a neutron are bound by a force known as the strong force, and it turns out these quarks have small electric charges. If the strong force binds them together at an effective angle from each other, the neutron will have an electric dipole moment, which is just a fancy way of saying the neutron will be net neutral, but with slightly more positive charge on one end and slightly more negative charge on the other. In the lab, physicists have measured the neutron's electric dipole moment to be almost exactly zero, which constrains the so-called theta angle of the strong force to be smaller than 1 part in 10 billion. The reason for this tiny theta angle is unknown, and this confusion is called the strong CP problem. One possible solution to the strong CP problem is to postulate a new particle known as an axion. And it turns out that axions can also be quite generic in theories of quantum gravity, such as string theory. Even better, axions can naturally explain dark matter, since they do not interact very strongly with light. This makes them an exciting candidate particle to look for, since just one simple addition to our theory can solve multiple open problems. Over the past few years, my collaborators and I have worked to better understand how axions behave cosmologically, with a particular emphasis on how an axion's interactions can affect the distribution of dark matter. One major discovery has been that axion dark matter can clump together in the early universe. This has potentially observable effects, ranging from changes to the ways the first stars form, to gravitational lensing of distant stars, to observable signals in laboratory experiments here on Earth. In the next decade or so, experimentalists will search for these effects, and the results should shed more light on whether dark matter really is an axion. We know more about the universe today than we have at any other point in human history, but there are still many exciting questions to answer. My job as a theoretical physicist is to help clarify the possibilities and suggest relevant experimental probes. It takes a while, but bit by bit, we're uncovering the most basic laws of nature, and I'm looking forward to seeing what new understanding is right around the corner.